Okay, let's turn the homework in. I'm going to go ahead and do 54 and 57, if that's okay. Okay, pass them on down. So with 54, so it says a $2,000 is an investment account with APR of 3.4% compounded continuously. So that means every year our money's going to go up 3.4%, right? No. So what it means is that we have to combine that 3.4% with every compounding every moment. It also does not mean that it's going up 3.4% every moment. It doesn't mean that either, because then at the end of the year you'd have an infinite amount of money. But what it does mean is that you have to take that 3.4%, combine it with continuous or moment-by-moment compounding, and then there's some equivalent true percent increase that you get by the end of the year. So I'm going to start with B. We'll just write that function. So our continuous growth form is A e to the RT. So A is our initial amount. Okay, E is that number, 2.71828, etc. What is R? 0.034. So it's the continuous rate as a decimal to the T. Okay, so that's the function that models the growth of our money. So how could we get the account value at the end of 5 years? Yeah, so that's an easy one. So we just take A of 5. A of 5 would be the answer to A. Okay, the APY. So the annual percent change, we just said, it's not 3.4%. Is it more or less than that? A little bit more, because we've got the compounding effect. So in order to do that, we want to rewrite, to find out what it truly is, we want to rewrite this formula in our original form as a B to the T. Okay, so it's still exponential growth. It's just a new way of looking at it with this new thing called continuous compounding. Okay, but it's still the same type of growth that we've had before with just the repeated multiplication of the growth factor. So to find the true percent increase, we just need this number B. So remember that the A's match up and the T's match up, which means that B equals what? Yep. Write it big. It's really important. So B equals e to the r. But if b equals e to the r, these are the exact same function. They're just in a different form. So we can get that value of b. It will be e to the 0.034. And that turns out to be 1.0346. So notice that B and R are like apples and oranges. They're not the same type of number, but they're very closely related. R is what? It's a rate. It's the continuous rate. B is not a rate, but what?
Growth factor.
Growth factor, right? It's the multiplier. It's what you multiply an output by to get the next output. And from that multiplier, we can get the true rate of increase, which is what? So what is our percent change? 3.46% change, or percent increase. And that's correct. That's what we said, a little bit more than the 3.4%. So that's the APY. That's the APY, the true percent change per year. What does that value represent? The true percent change per year for a continuous rate of 3.4%. That's the APY. Okay, the percent change over 10 years. Okay, well, we just take the percent change for 1 year and multiply by 10. Right? No, right? We said percent change doesn't work like that. What's the key transition to get from 1% change to another? How do we? Growth factors. So we've got the percent change for 1 year. So the first thing we want to get is the growth factor for 1 year. Here. That's the 1 year growth factor. And then from that we can easily get, what would our multiplier be to get the amount 10 years later? It would, yeah, I think every year you would multiply this. You'd multiply your amount by this number. So after 10 years, how many times will you have multiplied by that? 10 times. And that's what an exponent's for, repeated multiplication. So we've got the 1 year percent change to the 1 year growth factor to the 10 year growth factor, which equals, is that 406, 1.406? If I remember correctly. And now from the 10 year growth factor, we get the 10 year percent change, which is 40.6%. Okay, questions on number 54? Does it make sense? Yes, sir?
If we found the APY a different way but got the correct answer, will it still be marked as right?
Would you? You should know. You should definitely understand this way and be able to do this way.
I understand it, but I was just asking if we
no.
wrote it down.
No.
Okay.
No.
Thank you.
So what did you do? You divided two successive years.
I just did. I plugged 1 in for t, solved, then I subtracted the initial, and then divided by the initial.
Yeah, I mean you're just. Yeah, that's fine.
Okay.
You're just doing a more roundabout way of this, but yeah, it's fine. Totally fine. Other questions on this problem? Does it make sense? Okay, so then 57. So continuous, so first of all we got decay, and it's giving the continuous percent rate of 11.4%. So is that saying how much we're keeping every 1,000 years, or how much is going down every 1,000 years? How much is going down every 1,000 years? So we have to convert that into the value of R. So if we're going down 11.4%, well, that's the continuous rate, right? So the continuous rate is decay of 11.4% continuously. What is our corresponding value of R? No, so R is in effect, so that's like you're talking about like a factor, a decay factor. R is the rate.
Negative 0.11.
Yeah, so if it's decay, we said last time, negative, and it's how much it's going down. So, as a continuous rate, if it's growth, R is positive. It's the amount of increase as a continuous rate. And if it's decay, then it's negative. It's a rate. Okay? So, does the carbon truly go down 11.4% every 1,000 years? No, this is the continuous rate. So, this rate combined with moment-by-moment compounding, or moment-by-moment compounding, results in the true decrease of the amount of carbon-14. Okay, so to find this function, we can say t is in thousands of years, so the amount of carbon-14. We want to start by doing our continuous form. What's A? 150. We know what R is now. Negative 0.114 t. But we got to remember that t is in thousands of years. So if t is 2, that means what? 2,000 years. Because every 1,000 years we have this continuous rate of 11.4. So the question is talking about define the function that gives the amount at any moment. So even though our t is in thousands, it doesn't mean that this function is only going to... It doesn't mean that that function is only going to give these moments in time. Oh, just decay, right? Sorry. Okay, so it's decay, but just because t is in thousands doesn't mean that this function will only output discrete points like this. We can have fractional values of t. We can have t be a half, or a hundredth, or whatever. So it's still a moment-by-moment function. It's just that our units of t are thousands. So it's still a moment-by-moment function. It's just that t is in thousands. Okay, because we can make t 0.001, and that would be for 1 year. And we can make t 0.5, and that would be the 500-year mark. And it will still, this function will still accept, fraction and decimal versions of t, making it a moment-by-moment function, even though t is thousands. Does that make sense? So the fact that they said moment-by-moment doesn't mean that you have to change the unit out of the thousands. Because even if you changed it to years, well, that still wouldn't be moment-by-moment, right? Or days. So any unit's fine. And just consider that you can have non-whole numbers for t, and then you get the growth, or you get the value at any moment. Okay. So what is the percent change every 1,000 years? Negative 11.4%, right? Incorrect. How are we going to get the true percent change? Which would equal what? What kind of thing is that? Yeah, the decay factor. B equals e to the r. So find e to the negative 0.114. And what do you get? What is it?
0.892.
What does that number mean? So you need to know what that number means. How much we keep every 1,000 years. Is it a true, accurate amount that we keep? Or is it close? No, this is the true growth factor, right? So the one that's close is the one that has the R has to be combined with continuous compounding. But then once you get the B value, that's the true decay factor. And from that true decay factor, we can get the true percent change. How do we get that? Subtract it from 1. And now it should be close to that 11.4, but not quite. 10.8?
Yeah.
So the true percent decrease every 1,000 years, it's really going down 10.8% for a continuous rate of 11.4%. Why is the amount of decrease less than the actual continuous rate? That's kind of a hard question, but an important question. Why is the actual, so if it's a continuous rate of 11.4%, why does it only go down 10.8% truly?
Isn't that the same principles of compounding?
Mm-hmm. So what happens halfway through the 1,000 years, we've decreased, and we have a smaller amount of the carbon. So taking that same percentage moment by moment of a smaller amount is going to be a smaller decrease. So the cumulative effect will be less of a decrease because throughout those 1,000 years, the amount went down.
So if you were to graph this, as you go add more time, the graph becomes less steep.
That's right, just like this. Yeah. And so because we're taking this percent of the amount, but the amount is decreasing, then the amount of decrease is also decreasing. So the cumulative effect is to have less of a decrease than this 11.4%. Okay? Percentage change every 5,000 years. Just take this and multiply by 5. Right? Nope. Instead, we need to work through what?
5,000 year growth.
Need the 5,000 year growth factor, which we can get by taking the 1,000 year and doing what? Timesing it together 5 times. So watch out for timesing it times 5. That's not right. Timesing it together every year to get the next amount of carbon, we'd multiply by 0.892. So over 5 years, we'd multiply by it 5 times. What's that?
0.565.
0.565. So therefore the percent decrease. Is that 43.5? Right? You're gonna take that's what you keep, so what you lose is 1 minus that. So the true percent decrease over 5,000 years would be 43.5%. It's consistent over negative. So the same principle here. If in 1,000 years it goes down this much, in 5,000 years, look, it's going down less than 5 times that. 5 times that would be over 50%. It's going down less because over the 5,000 years, your amount gets less. So the same percent of a lesser number is a lesser amount. So the cumulative effect is that it will go down less. Okay, questions on 57? Lots of important stuff that we covered in that problem. Yes, sir?
Actually, on the previous, it's the same question as this.
Okay.
On the previous problem. When you take it from the 1 year growth factor,
Mm-hmm.
the E number, and you change it to like a 10-year, when I did it as E raised to 0.034 times 10, as opposed to actually taking the growth factor itself and raising it to 10. It's just a slightly different number.
It's because, I mean, basically, it's this. So you're taking the 10th power, the same thing. It's just that you probably, when you did B first, you probably rounded that number and then took it to the 10th. Whereas if you just leave this number in your calculator and take it to the 10th, you'll get a slightly different number. So you probably found it a rounded version, and that's why the results come in. But they're the same. They're the same. Right? Does that make sense?
Yeah, the number I have is just, I mean, it's a 0.1 difference, between the point. It's close.
It's just in the process, it's a rounding error. But they're the same. B to the 10th is the same as E to the R to the 10th, because B equals E to the R. Other questions about 57? Okay. Let's go on to new stuff here. Okay, so we're going to cover logarithms. So some of you have had logarithms before, and I want to kind of try to help you give a slightly different way of thinking about it that is intended to help you. So Don't check out and wait for the punchline. Okay? I'm giving you the punchline the whole way. So try to track with me. And if you've done them before, just give this a shot, because I think eventually you'll appreciate it more. Okay, so exponential. Let's just do a review example here. If a bacteria population started with 630 and grew 45% every day, determine the 1-day growth factor, the function, and the number of bacteria at 10 days. Go. Review. We should all get 100% on that. One-day growth factor, piece of cake, right? Everyone knows what it is. 1.45. Okay, function. We should all be able to do this. (630), 1.45 to the x. Okay, number of bacteria at 10 days. 10 days is represented how in this equation?
As x.
Okay, so again, to review before we just turn off our brain and just plug and chug, you should have a solid image of the exponential growth behind this thing right here. So let's review that. 630 is how much we have when? At day 0, okay? So how would you get the amount that you had on day 1? Which is what?
1.45.
Yeah, multiply by 1.45, and that gives us how much we have on day 1. And what could we do to that to get the amount on day number 2?
Multiply it by the same thing.
Multiply it again, right? So to get the amount on day 10, what will it look like?
10, 1.45.
10 of those multiplied by the 630. So that's what should be quickly going through your brain, this kind of idea, as you're using this function. But we don't want to write out 10 1.45s. That's why they're called exponential functions, because exponents allow us a short way to write repeated multiplication of the same number. Okay? That's review. Same situation, same function, new question. How many days will it take the population to grow to 500,000 bacteria? So now, the 500,000. Is that x? What's the 500,000? P, right? Or the output of the function. So now we know the output of this function, and we're asking about what the input is. Okay, so we can put that 500,000 in for the output, and we're asking what x is. So our first step, divide by 630, and that is 793.65 equals 1.45 to the x. Okay, and our goal is to figure out what that x is. So as we've just entered into algebra mode here, we kind of like hit a wall. It's like, what do we do? How do we solve for x if it's an exponent? Okay, so many of you know that that's something to do with logs, okay? And that's true. So let's just talk about what this is. What is x? X is the exponent of 1.45 that gives 793.65. This is the punchline, okay? This is the punchline today. X is the exponent of 1.45 that would result or would give 793.65. So it's just that we want a more complex way of writing that out. Okay? So we write it this way. This is what this means. The log base 1.45 of that number is the exponent of 1.45 that gives 793.65. Okay? So the purpose of a log is to solve for an exponent. That's true, but more than that, and more importantly than that, logs are exponents. Okay? Logs are exponents. This log right here, what does it represent? It's the exponent of 1.45 that gives you 793.65. So this phrase right here, this is what we're going to practice a lot. Okay? Again, so don't turn off your brain and say, I'm just going to wait for the formula at the end. Okay? This is what it's about. Okay, so this number, this exponent of 1.45 that gives 79.365 is 17.97. Okay? And we'll explain how to get that value later. We want to practice this idea of logs first. Okay? So here, this is the key. Logs are exponents. When you see a log, you should think, that's some exponent. Okay, so let's see how this works out. So this is the same thing we had before. And now we're saying that it can be written this way, as this log. This exponent x can be written as this log. And both these statements are saying the exact same thing. Again, this is the key. X is the exponent of 1.45 that gives 793.65. Okay, so on the left side, here's how that works. There's x is the exponent of 1.45 that results in 793.65. Does this make sense? You see it? So the other side says the same thing. It says x is, or x equals, and that thing on the right is, again, it's the exponent of 1.45 that gives 793.65. Okay? Logs are exponents. They're more than just a way to solve for exponents or something that has to do with exponents. No, logs are exponents. Okay? And these numbers are qualifying which exponent it is. Okay? So another way to say it is the log base 1.45 of 793.65. But the meaning is the more important thing. The meaning there that's circled is the more important thing. Okay, so you're going to practice. Practice putting these words onto these logs and then using the words to rewrite it without a log. Okay? So the first thing you're going to do is, use a phrase to say, what exponent is that? If it's a log, it's an exponent. So you're going to tell the person next to you, you're going to say, it's this exponent. And based on that phrase that you say, rewrite it without using a log. Okay? So, go. Find a partner. What exponent is it? I'm not asking for a number, so I'm not asking for an answer. I'm asking for a phrase that describes what exponent that is. And then based on that phrase, can you rewrite it without the log? Okay? Go. See if you can do it. Half the people in the room should be talking right now. Find a partner. Okay, so if a is a log, then it's some exponent. Somebody tell me what exponent it is. I'm not asking for an answer, not for a number, but what exponent is it?
It's the exponent of 5 that equals 25.
He said it's the exponent of 5 that would give 25. Agree with that? Yep. That's what we're going to practice, okay? Don't skip over it. This is the whole heart of it. And now, based on that statement, how could we rewrite that without a log. If a is the exponent of 5 that gives 25, what could we say? 5 to the a equals 25. You see? And we all know what that a is then. 2, right? So since a equals 2, that's talking about the exponent of 5 that would give 25, which is 2. Does it make sense? Okay, practice it again. So, first say the word statement, and then use the word statement to write another mathematical statement without a log. Go. Okay, someone in the back, what exponent is z? Someone in the back. Yeah. He's catching on. He's catching on. It's the exponent of 2 that will give you 16. Okay? So if z is the exponent of 2 that gives 16, how can we rewrite that without a log? 2 raised to the z would be 16. Okay, and what is, so we know this one also, what is z? 4. So what number raised, what number, if 2 was raised to it, would give 16? That's 4. Okay, one more. Go. Statement, and then mathematical statement without a log. Tell the person next to you. Practice. Yeah. Please. Everyone's here? Yep. P is the exponent of 4. That would give you 1 over 64. Okay, so can we write that as someone else? How can we then rewrite that without using log? He wants 4 to the p equals 1/64. Is that right? Cool. So now if we wanted to try to solve this one, if you notice the denominator there, 64, is 4 cubed. So what would p be? -3. Okay, so this is what, whenever you see logs, practice this. Because then if you get this, there's nothing to memorize. So some of you in the past may have memorized something where, oh, okay, so I put the 4 here, and then I put the p there, and then I put the 160, like this, you know? Okay? But you never have to worry about screwing that up if you just understand what a log is. If you really understand what a log is, then it just naturally, you just say the statement, and you can write the exponential form. Okay, so more practice. Page 1. So I want you to do the same 2 steps. Page 161. First step, number 2. Page 161, number 2. Page 161, number 2. Same 2 steps. First step is So new instructions. Ignore those instructions. Step 1. Describe each log in words. Okay? Based on those words then, rewrite a mathematical statement without the log. Compare what you have so far with the person next to you. Talk it out. So just whatever you have so far, check it. Okay, if you got questions, stop me. Come on. Yeah, sure. What exponent is it? That's not what we're concerned about right now. We'll do that later. So just focus on this. Just describing those words and then rewriting them as a. Yeah, I wanted you to practice either writing or saying the words of what the logs mean first. And then based on the phrase. That's equivalent statement. The words are what exponent is the log. That first one, what exponent is that log? Okay, is there one you want me to talk about? Request. G? Oh, J. Okay, great. All right, so this one. So if it's a log, what is it? It's an exponent. So what exponent is that? So this is the exponent.
3 is the log of e
e to the third power equals that.
No, describe to me what exponent that is. That's what I'm trying to get you to do. Look, when you see a log, I want you to be able to see that it's an exponent. Particularly, what exponent is it? It's the exponent of e that gives you x. And according to the statement, what is the exponent of e that gives x? 3. So 3 is the exponent of e that would give you x. So now we can rewrite it. So 3 is the exponent of what? E. That will give you x. 3 is the exponent of e that would give you x. Right there. 3 is the exponent of e that would give you x. Any others that we want to go through? I. Okay? Is that a C? Okay. So, can you tell me what exponent, logs are exponents? Can you tell me what exponent that is?
The exponent of C.
The person who asked for this? Who asked for I? So what exponent is that? No, I'm asking you what exponent is this log right here? What exponent is it? Resistance. The exponent of C. That would give 81. That's the key. If you can do that fast, then rewriting is no problem. It's the exponent of C that would give 81. And we know in this case that's 4. So if 4 is the exponent of C that gives 81, how do we rewrite it? 4 is the exponent of C that equals 81. Okay, so some important things. So look at G. Our number system is based on tens, right? The places and the numbers that we have are tens. Hundreds, thousands, right? It's all based on 10. So this is a special log, base 10. So it could be this could be rewritten as a log without a number. So if you ever see a log without a base, the implication is that it's 10 there. Okay? This is important. So what exponent is the log of 19? What exponent is the log of 19? The exponent of 10. That gives 19. So this right here is the exponent of 10 that would give you 19. Because there's no number here. So if there's no number there, it means 10. Okay? So that's base 10. The other important base that we saw was, starting last time, we talked about with continuous compounding. We had base E. So, right, because base E is a very important base. It also has a shorthand notation. It's called natural log. And so the shorthand for log base E is ln. So this statement in J could be ln of x equals 3. It's the exact same statement. So whenever you see ln, that's an exponent with what base? Okay, so describe that to the person next to you. What is that? So it's ln 52, obviously, but describe it as an exponent. Go. What exponent is that?
Exponent is what we give.
It's the exponent of e. That would give 52. So how could we write that? So we could call it, say, d. And how would we? So d is the exponent of e. That would give 52. So if d is the exponent of what? E equals 52. Same thing. So your calculator then has those two logs built in. These two special logs. The log base 10, it's just the button that says log on it with no number. That's your log base 10. And then there's a button on your calculator that says ln. It's natural log. Those are the only two logs that your calculator can solve for, automatically. So what we want to know is how do we solve for actually get the value for other logs? For instance, this one here. What exponent is m? The exponent of 7. That would? Okay, so let's think about that. What number would m be? If 7 to the m is 12, can you make an estimate of what m would be? About what? Between 1 and 2, right? Because 7 to the 1 equals 7, and 7 squared equals? So this value m, closer to 1 or closer to 2? We think it would be closer to 1. But here's the problem. Your calculator doesn't have base 7 built into it. It doesn't have base 7 built into it. So how can we get our calculator to give us a good approximation for this exponent of 7 that would give us 12? Here's how. So we've got x is the log base 7 of 12, right? And we think that this is going to be something like 1 point something, close to 1, okay? So your calculator only knows base e and base 10, so we need something that's called the change of base. And the change of base allows us to do this. Log base 7 of 12, we can calculate it as, we can change the base to 10, we can do the log of 12, so that's base 10, over the log of 7, the original base. Okay, so if you do that in your calculator, we think we should get a number between 1 and 2, but closer to 1. Do it. So log 12 over log 7. What is it?
1.276.
1.276?
Yeah, 12.277.
Okay, so you can change the base to anything you want. So the other base that your calculator can do is e. So if you do ln of 12 over ln of 7 on your calculator, you ought to get the exact same number. Because the change of base formula allows you to change the base to any base, as long as you're consistent in the numerator and the denominator.
Yeah.
Same thing. So if you have a base other than 10 or e, and you want to get a good approximation, you need to use this formula, which says change the base to anything you want, and then do the log of the number over the log of the original base. And that will give you then, this is what is this? The exponent of 7 that would give 12. The exponent of 7 that would give 12. Anybody have a question on that? Okay, so I'm going to post a reading workbook shorter assignment for Friday. It'll be up today. Only Wednesdays. Just Wednesdays.